Thank you, and thank you all for your time. And the topic of the presentation is go climb a dependency tree and crack the grammatical errors. In fact, I think this paper is much more suitable to be put in the NLP application track because we do not propose new dependency parsing methods, but application of dependency parsing into the task of grammar correction. I'm the first author, Longkai, and this paper is co-authored with my advisor, Professor Houfeng Wang. So let's begin this talk. And I assume that some of you do not have a clear understanding of the task of grammar correction. So first, I will describe about the task, and then give the algorithm description, and then give the experiment results, and lastly some comments on how to implement the system. And now let's begin. First, about grammar correction. In fact, it's hard to give a precise definition of grammar correction here, but I can compare this task with the task of spell error correction. I think spell error correction, we usually made this problem in our use of search engine, like you may have some typo in your query into the search engine, and the search engine may reply to you that what you're looking for may be something else, like a typo in your query word. Well, for grammar correction, things may be a little bit different. Usually, we do not use wrongly spelled word. In fact, the words sometimes have the right meaning, but from grammatical point of view, it's ungrammatical. Like the two examples I show here. The first is I is a voice, which the verb is should be corrected into to am, and boys should be corrected into boy because it's a plural form. And the second example is book is up the desk, where the first word of the sentence should be the, because the book is a noun, and we should put the in front of the book, and the preposition up is wrongly used because we should use on the desk, not up the desk. In fact, in some languages, like my mother tongue Chinese, we do not use articles, I mean and the in Chinese. Therefore, when we learn English and try to write sentences in English, we usually omit the and the in the sentence, and this is a commonly made mistake by second language learners. And this is the basic description of the task. So when we refer to the task of grammar correction, one data set we should refer to is the Kano 2013 shared task data, and the current systems for the task are all perform the experiments of the task of the methods all perform experiments on the data of the shared task, and there are 5 kind of errors commonly considered in the task of grammar correction. Like I list them in the table. They are the article and the determiner errors, which usually mainly considers the errors related to and the, and the preposition errors. And non-number errors usually refer to the plural and the singular errors in the noun form, and the verb form errors usually consider the errors in verb. And the last one is the subject and the verb agreement error, which also considers the errors related to nouns and verbs. Some of the errors I give some example. And then usually the experiments of recent years methods for grammar correction are performed on this data set. And the methods used by the current system, usually I can sum this up into the 3 categories. The most prevalent one and is used in most systems is the pipeline system, which try to crack the grammatical errors in a pipeline style, and they train individual classifiers or individual models to correct each kind of error. And the input of one part of the system is output of the previous one. And you can see that this kind of methods is easy to implement and easy to extend to other kind of errors, but it's difficult to stop the errors from the early age to the next stage. To the next stage, like there are some errors may interact with each other, like the subject and the verb agreement errors are also related to the verb errors and the non-number errors. And another way of dealing with the task is to view the whole problem like a translation problem. I mean, the method can view the error sentence as the source language and will use the correct one as the destination language and build translation models from the source to the destination. And one difficulty for the translation models is that to train a reasonable translation model, you need large number of training data, and for the training data, it's not easy to automatically generate. And in recent years, there are also methods about joint inference which do not view the correction problem as a pipeline problem, but tries to get a globally optimized result using the joint inference. Like in recent years, the interlinear programming methods, IRP method, play an important role in the grammar error correction tasks. And in last year's CCL and EMRP, there are 2 papers about the IRP-based method for the joint inference. And they all reached a reasonable result. But for IRP, we require that you should enumerate all possible corrections of all kinds of errors, or at least subcategory. I think at least you should enumerate part of the corrections. Therefore, the decoding is sometimes very slow, and you understand that for IRP, the worst case in time complexity will reach exponent, and although it's a bit slow and a bit complex, the IRP by last year it shows the best performance. So what does our methods do? Our method comes from intuition from the spell checking problem. I give an example in the spell checking problem where the two of the and usually because in the keyboard E and W are located close to each other, you usually when you type THE, you may add a W after E and form a typo. Therefore, the correct one should be two of the. Therefore, you can view this spell checking problem as 2 steps. And first, you generate correction candidates for each word, and then find a path from left to right to maximize the overall score of the path. And the weight of the age can be measured through a language model, such as in this example, the borderline is a path with the maximum score. And if you are familiar with graph theory, you can see that this problem can be tackled easily through dynamic programming from left to right. But this model cannot be directly adapted into the grammar error correction task. I'll give you an example below. What about this one? The books of that boy is on the desk. Well, from this word sequence we can see that boy is on the. They are quite reasonable because boy is a singular noun and is also singular, and they can be together. In fact, in this sentence, books is the subject of is. Therefore, this sentence is not correct. But this kind of linear chain method can fail in this situation. So what's the solution? The solution is like this. We can see the dependency tree of the sentence. This is the dependency parsing result from the Stanford parser. And if we look into the node is directly, we can see that the is has 2 direct children. The first is books and another is on. So if we look at if we consider the node is only, the text will be books is on. Well, the probability of books is on is much less than the probability of books are on. Therefore, we can, by doing this, we can think that it may be some grammatical errors in the sentence. So what we need here is just a language model trained on the node text. In the original sentence, we can only evaluate the correctness of each n-gram just in the word sequence in the linear chain level. But on the dependency passing, in the dependency tree, we can evaluate the correctness of each n-gram on the node directly. We named the language model as tree node language model in the paper. And so how can we get the node text we refer to as sub-sentence in the paper? Well, I give a longer example. The car of my parents is damaged by the storm. Well, if we want to train language model, we should have a text corpus. And if we want to train the language model on nodes, we also need a collection of sentences. And the collection of such node text can be collected from the nodes. I mean, if you look into the node damaged here, and it has 3 children. The first is the car, and then is, and the by, and with itself, they are totally forwards ordered by their original order in the sentence, and therefore you can get the sub-sentence, car is damaged by. And if you collect every node in the sentence and collect every sentence in the corpus, I require the sentence should first have the part structure. And you can build a new corpus and train the ordinary language model, just like you train the basic language model, and do not need to modify any code. So about the decoding problem is that given each node a list of correction candidates, and how to select the candidates for each node to maximize the overall correctness score of the sentence. Well, it sounds at least we can enumerate all possible corrections candidates and then find the maximum score. But this is time consuming. Recall what we do in the linear chain style, where we can use dynamic programming from left to right to efficiently calculate the path with the maximum score. Well, in the tree, in fact, the linear chain is a special case of the tree. In the tree, we can still do the dynamic programming, but not from left to right, but from bottom to up. It means from leaf to root. So the details of the dynamic programming I have listed in the paper, and I will not refer to in here. And let's come back to the table, and there are 5 kinds of errors. What we said just now can correct most of the replacement errors. When I refer to replacement errors, I mean the errors that you can correct by replace original word to another one. But this kind of errors can cover most of the errors related to verbs and nouns and subject verb agreement, and even some errors in the preposition, because you may use a wrong preposition. But in preposition and determiners, you may omit or there may be some omission or reduction of the prepositions. You may need to add or delete existing preposition. Therefore, special models should be proposed to solve this. And the method we use is also on the dependency tree, which try to give each. Here. So we build classifiers for the determiners and preposition errors for the special model, and the distinctions are made at the node level directly. For example, for the determiners, we will decide whether the current non-node means the node is a noun, should have an article, and if we should have an article, which one is it? If the non-node already have article and the prediction is it should have another article, then this means that you should correct the original article to another. So about experiments, so if we want to train a reasonable language model, we should use the past gigaword. In our system, we use the past gigaword. And the development we use is the training data given by the Kano 2013 share task. In fact, in the share task, do not limit the resource each system can could be, and they provide a limited number of training data to turn the parameters. And the test data we use is just the test data in this shared task. And this is comparison with the state of system, and the performance measured in the F1 score. Detailed description of the L1 score F1 score can be found in the shared task description paper. And the first three are the top systems in that shared task. And the first one is the pipeline. And the fourth one is the state of art. By last year, it's interlinear programming-based method. And our method can outperform the state of system. And the results of each, in fact, our method is the pipeline-styled method, which is divided into three parts. The first is the language model part, and then determinant part, and the preposition part. You can see that each part plays its own role. And for the language model part, our trained language model is better than ordinary language model on the linear chain. So some implementation details. The first is past corpus. Well, it's quite time consuming. I think everyone here is quite familiar with parsing, but if you want to get accurate dependency parsing result, the parsing is quite time consuming. Usually we passed about millions of sentences, and it costs so many days to pass it. We use multi-thread and finally got the result. And the second is about scores and the probability. The only difference between the scores and the probability is that probability is normalized. Where in our task, in the task of grammatical correction, we do not need to know the exact confidence score, and we only want to know the maximization. Therefore, we usually use scores instead of probability, because you can set the preference of the original words. Usually, we think the original word tend to be correct, and we do not correct the original word unless it's much more confident than some threshold. Therefore, if you use scores, you can add some extra parameters to control the preference of the original word. And there are also some constraints for the verb tense. Like, because in this framework, we cannot solve the problem like this. If the sentence says I was a student, but I was a student has a much lower probability than I'm a student. Therefore, it tends to correct the I was a student into I am a student, although the correction is wrong. Therefore, in our system, we require that the verb tense should not, the tense of the sentence should not be corrected. But I think there might be some better ways to handle this problem, like you should find the verb, the tense information between sentences and use some constraints for this. But this is not covered in this paper. And lastly, one question everyone asks me when I talk about my paper is that how dare you use the dependency parsing result of an ungrammatical sentence? Well, some may believe that if the sentence is ungrammatical, the parsing result is not reliable. In fact, in our method depends on the dependency parsing result, but in most cases, the result is the situation not serious. I give an example of the same sentence. The books of that boy is on the desk, and the books of that boy are on the desk. In fact, the results are from the Stanford parser. You can see that the trees, they have the same tree structure, but the only difference is their post tag and the word. Therefore, if the relation of the words are basically correct, and you can perform this method on the dependency tree. So that's all my presentation, and thank you.
We have 5 minutes for questions, so are there any questions? No questions? There we go, on.
Thanks. So in your work, you use Stanford parser, right?
Yes.
But Stanford parser use something like Stanford dependency annotation. So did you try, your system with, another kind of dependency annotation, something like using Yamada and Matsumoto head rules, or?
No, you mean other types of dependency relations,
yes,
right?
Yes.
No, we just use the dependency parsing of the tags used by the Stanford parser. We do not try other kind of tags. Yeah.
Okay, thanks.
So you preempted my question with your slide. So that was a good slide. But actually, there's one follow-up on that is that in your case, this was just an agreement between the subject and the verb.
Yes.
But if you have, for example, a typo in a preposition, then the parser will probably be pretty lost. Have you seen any of those cases, or is it typically not a typo but just a wrong preposition?
Usually, if you use incorrect agreement or use incorrect verb form and noun numbers, they will not affect the relationship between the verb and the noun. I think in my experience, there are some sentences that with the incorrect structure, but they will not affect the verb and the noun relationships. But they are just a wrong dependency tree. And the relation, like you attach the preposition to the incorrect position, but this will not affect the overall score.
Okay. And then have you considered using some type of morphological analyzer that would tell you that books is plural and that is singular, rather than having to model sort of the language model score?
In fact, the non-number error is corrected in the language model part, and the extra special model is specially designed for the article and the preposition. So about non-number, they are incorporated in the unified framework in the language model.
Okay.
Yes.
Any other questions since we have time? No? Okay, well then let's thank the speaker again and take 2 minutes to set up. If you want.